In this model, the error term ET is serially correlated, as you can see from equation 2. ET is equal to phi ET minus 1 plus VT, where VT, however, is serially uncorrelated. That is, VT is uncorrelated with its past or future values. This model is called a model of first order autocorrelation. Why does serial autocorrelation arise? Typically because of two reasons. One, because the regression equation is misspecified, or two, because of seasonality in the data. How does serial autocorrelation arise through misspecification? Look at the following diagram. On the y-axis, we have per capita agricultural output across various districts in a country. On the x-axis, we have annual rainfall in each of these districts. Now it is possible that as annual rainfall increases, per acre output increases up to a point and then falls. So the relationship between per acre output and annual rainfall is not linear, as you can see in the scatter diagram. However, suppose we specify a linear relationship given by the red straight line. You can then see that all the points in the blue circle above the red line will be positive, whereas all the points in the red circle below the red line will represent negative error terms, which means that if a given error term is positive, it is likely that the error terms immediately next to it are also likely to be positive, and if a given error term is negative, it is likely that error terms immediately around it are also likely to be negative, which will induce a correlation in the error term. So if we know that a given error term ET is positive, you would expect ET plus 1 also to be positive, whereas if you expect ET minus, if you know that ET minus 1 is negative, you would expect ET to be negative as well. Another reason for serial autocorrelation in the error terms of a regression equation is because of potential seasonality in the data. In the graph below, let y-axis represent sales of a particular commodity in month I, whereas on the x-axis we have price of the commodity in that particular month. Overall, as you can see, the relationship between them is negative. But suppose every 6 months, the sales of the commodity are particularly high relative to the linear regression line. So every 6 months, you would expect the error terms to be positive, which means that if ET is positive, ET plus 6, ET plus 12, ET plus 36 are all expected to be positive. This means that you have seasonal correlation in the error term, which can induce serial autocorrelation. What is the impact of autocorrelation in the error term? A. Despite of autocorrelation, the OLS estimator for beta hat will continue to be unbiased and consistent. Remember, unbiasedness or consistency are not possible only if the correlation between x and the error term is not equal to 0. Here, X is not correlated with the error term in model 1. It is the previous values of the error term which are correlated with their future values. So the correlation is in the error term itself and not between X and E. Therefore, the OLS estimators continue to be unbiased and consistent. The problem is that the variance of beta hat OLS is no longer sigma square upon summation xi minus x bar square as it would have been had the correlation between error terms been equal to 0. So why does autocorrelation matter? The OLS estimators will continue to be unbiased and consistent even if there is heteroskedasticity or autocorrelation. However, in the case of autocorrelation or heteroskedasticity, the usual standard errors of beta hat OLS, that is sigma square upon summation xi minus x bar square, will be incorrect. Hence, hence the t values based on the usual standard errors will also be incorrect. So what does one do about this? One strategy is to transform equation 1 in such a way that the error terms in the transformed equation are no longer serially autocorrelated.
So this will take us to the generalized least square model, where the generalized least square model is actually the linear regression model with an impact on the OLS.
Transforming the model so that it satisfies the assumptions of the OLS, that is, the error terms are neither heteroskedastic nor autocorrelated, and then doing a regression on the transformed model is called the method of generalized least squares or GLS. So how does one achieve this? Think of the usual model. Yt is equal to alpha plus beta xt plus et, where Et is now serially autocorrelated, that is Et is equal to phi Et minus 1 plus Vt. There are two things to remember about this equation. The absolute value of phi is strictly less than 1. Secondly, the error term Vt in the equation for Et is serially not correlated. That is, we are going to explicitly assume that Vt is normally distributed with mean 0, a constant variance sigma square V, and the covariance of Vt with its past or future values is 0. Now since Et is correlated with Et minus 1, in this specific case, we say that this model has first order serially autocorrelated errors, or the errors follow an AR1 process. The point is to transform this model into one where the errors are not serially correlated. So consider equation 5, which is nothing but equation 1 lagged by 1 period. That is, if equation 1 had yt on the left hand side, in equation 1 had yt on the left hand side, equation 5 has yt minus 1 on the left hand side. So we have yt minus 1 is equal to alpha plus beta xt minus 1 plus et minus 1. Now consider multiplying equation 5 by phi. Here we are assuming that we know phi. So we have phi yt minus 1 is equal to alpha phi plus beta phi xt minus 1 plus phi et minus 1, which we will call equation 6. Now subtract equation 6 from equation 1. So on the left hand side, you have yt minus phi yt minus 1. On the right hand side, you have alpha minus alpha phi plus beta xt minus phi beta xt minus 1 plus et minus phi et minus 1. Now note that et minus phi et minus 1 is indeed Vt. We will call this transformed equation, equation 7. Now, equation 7 in the previous slide or equation 8, which is just equation 7 written more neatly, has an error term that is not serially autocorrelated. This is what we wanted to achieve. We wanted to transform equation 1, which had serially autocorrelated errors, into a new equation which now no longer has serially autocorrelated errors, so that we can apply usual OLS and the usual OLS standard errors, and the t-values will be applicable. But there is a critical assumption here. In order to transform equation 1 into equation 8, we need to know the value of phi. But in reality, we are unlikely to know that value. So we will have to find a way to estimate it. In other words, we'll have to find a way of making our GLS method feasible. Hence, what we are looking for is a feasible generalized least squares estimator. How does one achieve this? We will break the process into two steps. In step 1, we simply estimate regression 1. Remember, our estimates of alpha hat and beta hat, even from model 1, are unbiased and consistent. So we can go ahead and estimate model 1. After you estimated model 1, get y hat t, which is equal to alpha hat plus beta hat xt, and obtain e hat t, which is yt minus y hat t. After you've obtained E hat t, then do the regression of E hat t is equal to phi E hat t minus 1 plus Vt. Remember, this is a regression equation without an intercept, and hence the estimate of phi hat is given by summation E hat t minus 1 upon summation E hat t minus 1 square. Will give us an estimate of phi hat. Once you obtain an estimate of phi hat, then you simply substitute this in equation least squares estimator. So instead of yt minus phi yt minus 1, in the usual OLS you have format, yt minus phi hat yt minus 1. Y star. And instead of alpha into 1 minus phi, you have alpha into 1 minus phi hat. And therefore the beta instead of xt minus phi xt minus 1, you have xt minus phi hat xt minus 1 into x star t minus x star bar estimate of phi hat x star minus once you obtain an estimate of phi hat, you simply substitute this in equation beta hat and alpha hat, because so instead of yt minus phi yt minus 1, you have yt minus phi hat yt minus 1. The problem was alpha into 1 minus phi, you have alpha into 1 minus phi hat. That is instead of xt minus phi xt minus 1, you have xt minus phi hat xt minus 1. B upon summation x star estimate of phi hat bar the whole square. Once you obtain an estimate of phi hat, you simply substitute this in equation 8. So instead of yt minus phi yt minus 1, you have yt minus phi hat yt minus 1. And instead of alpha into 1 minus phi, you have alpha into 1 minus phi hat. How many gaps do you have? Instead of xt minus phi xt minus 1, you have xt minus phi hat xt minus 1. Divide this sum by n minus 3. Why n minus 3? Estimate because we had n observations We lost
Once
one
you obtain an
observation to the
estimate of
process
phi
of taking
hat,
a lag,
you
and
simply
then we have two
substitute this
parameters
in
that we have
equation
estimated.
A.
The degrees of freedom
So
here are
instead of
n minus
yt
3.
minus phi
If we had
yt minus
initially
1,
in model 1
you
n
have yt
observations to
minus phi
start with.
hat yt minus 1. And instead of alpha into 1
So
minus
consider
phi,
model as
you have
usual.
alpha into
Yi
1
is
minus
equal to
phi
alpha
hat.
plus beta xi
Instead of
plus
xt
ei.
minus phi xt minus
But
1,
when we assumed
you have xt
homoscedasticity,
minus
we
phi
said that the
hat xt
variance of
minus
each
1.
of the error terms ei was constant. So we
Give us
said
an estimate of phi
variance
hat.
of E1 is equal to
Once
variance
you
of
obtain an
E2 is equal to
estimate of
variance
phi
of
hat,
E3 and
you
so
simply
on, and
substitute
all
this
of them
in
were equal
equation
to sigma
A.
square. But
So
now we're
instead
going
of
to wait
yt minus
a
phi
change in
yt
that
minus
assumption.
1,
We're going to
you have
assume
yt
that
minus phi
each
hat
of
yt
the
minus 1.
error
And
terms
instead of alpha
have a
into 1
different
minus
variance.
phi, you have
So we're
alpha
going to
into 1
allow
minus phi hat.
variance
Instead
of
of
E1
xt
is equal
minus
to
phi
sigma square
xt
1,
minus
variance
1,
of E2 is
you have
equal to
xt
sigma square
minus
2,
phi hat
variance of
xt
E3 is
minus
equal to
1.
sigma square 3, and so on. And potentially, we're going to
Give us an
allow each
estimate
of
of
the
phi
sigma
hat.
square i's to be different.
Once you obtain an estimate of phi
So
hat,
under
you simply
heteroskedasticity,
substitute this
we
in
allow
equation
each of the
A.
error terms to have
So
a
instead of yt
separate
minus
variance.
phi yt minus
So the
1,
variance of E1,
you have
which is
yt
sigma
minus
square
phi
1, will
hat
be different
yt
from the
minus
variance
1.
of E2,
And instead of
which is
alpha
sigma
into
square
1
2,
minus phi,
which in turn
you
is
have alpha
different from the
into 1
variance of
minus phi
E3, which
hat.
is sigma square
Instead
3,
of xt
and
minus
so
phi
on.
xt minus 1, you have
This
xt
graph
minus phi hat
represents
xt minus
one
1.
particular type of heteroskedasticity where the variance
Give
of
us
the
an
error
estimate of
term
phi hat.
increases with the
Once you
value of
obtain an
x. You
estimate
can
of
see
phi
in the
hat,
picture that as
you
x
simply
increases, the
substitute
way
this
the
in
spread of the data
equation A.
expands. That is,
So
the
instead of
variance of the
yt
error term
minus
is not
phi yt
constant,
minus
but
1,
actually is some
you
function
have
of x.
yt minus phi
So just
hat
as in the
yt
case
minus
of
1.
autocorrelated
And instead of
disturbances
alpha
that we
into
have
1
seen
minus
before,
phi, you have
the
alpha
OLS
into 1 minus
estimators,
phi hat.
despite of
Instead of xt
heteroskedasticity,
minus phi xt
continue to
minus
remain
1,
unbiased
you
and
have xt
consistent.
minus phi hat
That is
xt
because
minus 1.
X and E are still uncorrelated.
Give us an estimate of phi hat.
And just as it was
Once
the
you obtain an
case under
estimate of phi
autocorrelated
hat, you
disturbances,
simply
the
substitute
impact of
this in equation
heteroskedasticity is
A.
in changing the
So instead
formula
of
for the
yt minus
variance of
phi
beta at
yt
OLS.
minus 1,
The variance of
you
beta at
have yt
OLS
minus
is
phi
no
hat
longer
yt
sigma
minus
square
1.
E upon
And
summation
instead of
xi
alpha
minus
into
x
1
bar
minus phi,
square,
you
but
have
will
alpha
now have
into
to
1
be
minus phi
changed.
hat. Instead of xt minus phi xt minus 1,
So then we can
you have
take two
xt minus
approaches to
phi
the
hat
problem.
xt minus
In the
1.
first approach, we allow the
Give us
error
an
term
estimate of
in
phi
equation
hat.
1 to continue to be
Once you obtain an
heteroskedastic
estimate of phi
in the
hat,
sense that the
you
variances
simply
of all the
substitute this
individual error
in
terms are not
equation A.
identical, and
So
then we
instead of
can
yt
modify the
minus
formula
phi
for the
yt minus
variance of
1,
beta hat
you have
to
yt minus phi
accommodate this
hat
feature,
yt
which
minus
will
1.
give us the
And instead
standard
of
errors
alpha
which are
into 1 minus
consistent with
phi, you have alpha
heteroskedasticity,
into
which
1
are also
minus phi
referred to
hat.
as
Instead of xt
heteroskedasticity
minus phi
consistent
xt
standard
minus 1,
errors.
you have xt minus phi
The
hat
other
xt
approach
minus
is the
1.
GLS approach, which consists of
Give us
modifying
an estimate
equation
of phi
1
hat.
in such a way that
Once
the
you
error
obtain an
terms of
estimate
the
of phi
modified
hat,
equation
you
no
simply
longer have
substitute this
heteroskedastic
in
disturbances,
equation
but
A.
in fact each of
So
the error
instead of
terms of
yt
the
minus
modified
phi yt
equation
minus
have
1,
identical
you
variances.
have yt minus phi hat yt minus 1.
So think
And
of
instead of
equation 1
alpha into
again,
1 minus
yi is
phi,
equal to
you
alpha
have
plus
alpha
beta
into
xi
1
plus
minus phi
ei,
hat.
but now
Instead of xt
each
minus
of the
phi
ei's
xt
has a
minus
different
1,
variance.
you
So
have xt
variance
minus phi hat xt
ei
minus 1.
is sigma square I for each I.
Give us an
Now
estimate
let's
of
make a
phi
heroic
hat.
assumption. Let's assume that
Once you
we
obtain an
know
estimate
each
of
of the
phi
sigma
hat,
square I.
you simply
I know this is
substitute this in
unlikely,
equation
but currently
A.
let's go with it.
So instead of yt minus phi yt minus 1,
So let's divide
you have yt minus phi
yi
hat
by
yt
sigma
minus
I.
1.
So we have
And instead
yi
of
upon
alpha into
sigma
1
I
minus
is
phi,
equal to
you have
alpha upon
alpha
sigma
into 1
I
minus phi
plus
hat.
beta xi
Instead
upon
of
sigma I
xt
plus
minus
ei
phi
upon
xt
sigma I.
minus 1,
Let's
you have
redefine the
xt minus
variables.
phi hat xt
Let the
minus
new
1.
yi star be yi upon sigma I. Let
Give
alpha
us an
star be alpha
estimate
upon
of
sigma
phi
I.
hat.
Let x star I
Once
be
you
xi
obtain an
upon sigma I.
estimate of phi
And let the
hat,
new error
you
term
simply
vi be
substitute
vi
this in
upon sigma
equation
I.
A.
So what we have done is
So
we have
instead of
actually
yt minus
transformed the
phi
data.
yt minus 1,
Now let us see whether it
you
solves the
have
problem
yt
of
minus phi
heteroskedastic
hat
disturbances.
yt minus 1. And instead of alpha
Yes, the
into 1
problem was that
minus
the
phi,
variance of
you
the
have
error
alpha
term
into
in
1
module
minus
1
phi
was
hat.
not constant.
Instead of xt
So the
minus
problem
phi
would go
xt
away
minus 1,
if the
you have
variance
xt
of the
minus
error
phi
term in the
hat xt
modified
minus 1.
equation is constant. So let us find out what is the variance
Give
of
us an
Vi.
estimate
Now
of
Vi
phi
is
hat.
EI upon sigma
Once you
I.
obtain an
You know that
estimate of phi
variance of
hat,
x upon
you
alpha
simply
is 1 upon
substitute this
alpha
in
square variance of
equation
x.
8.
So by the
So
same
instead of
token,
yt minus
variance
phi
of
yt minus 1,
EI upon
you
sigma
have
I will be
yt
1
minus
upon
phi
sigma I
hat
square
yt
variance
minus
of
1.
EI.
And
But
instead
the
of
variance of
alpha into
EI is
1
itself
minus
sigma
phi,
square I.
you
So you
have
would have
alpha
1
into
upon
1
sigma
minus
square
phi
I
hat.
into sigma
Instead
square
of
I, which is
xt
1.
minus phi
Which means
xt
that the
minus
variance
1,
of each
you
of
have
the error
xt minus
terms
phi
would be
hat xt
1
minus 1.
and hence constant. Therefore, the problem seems to have
Give
been
us an
solved.
estimate of phi hat. Once you obtain an estimate of
So
phi
beta hat
hat, you
GLS
simply
uses the
substitute this
formula
in
that the OLS
equation
uses,
8.
except
So
that
instead of yt
instead of
minus
using
phi
the
yt
original
minus 1,
variables xi
you
and
have yt
yi,
minus phi
we use the
hat yt
transformed
minus 1.
variables
And instead of
xi
alpha into 1
star,
minus
which is
phi,
xi
you have
upon
alpha
sigma
into 1
I,
minus phi
and yi
hat.
star,
Instead
which
of
is
xt
yi
minus
upon
phi xt
sigma
minus
I.
1,
So
you have
therefore
xt
beta hat
minus phi
GLS
hat xt
becomes
minus 1.
summation xi star minus
Will give us an
x star
estimate of phi
bar
hat.
into y star
Once you obtain an
minus y
estimate
star
of phi
bar in
hat,
the
you
numerator
simply substitute
and
this in
summation
equation
xi
8.
star
So
minus
instead of
xi star
yt
bar
minus
square
phi
in the
yt minus
denominator.
1, you have
You can
yt
always
minus phi
rewrite it in the
hat
form
yt
of the
minus 1.
original
And
x's
instead
and
of alpha
y's,
into 1
which you
minus
can
phi,
see in
you
the
have alpha into
blue
1
color,
minus phi hat.
where
Instead of xt
xi
minus
star
phi
I've just
xt
used
minus
xi
1,
upon sigma
you have
I.
xt minus
Instead of
phi hat
x
xt
star
minus 1.
bar, I've used summation
Will give us an
1 upon
estimate of
sigma
phi
I
hat.
into xi, the
Once
whole
you obtain an
divided by
estimate of phi
n.
hat, you
Similarly,
simply
for y
substitute this
star I've
in
used yi
equation
upon sigma
8.
I, and
So
for
instead
y
of yt
star
minus
bar
phi yt
I've
minus
used
1,
1 upon
you
sigma
have
I yi,
yt
the whole
minus phi
summation
hat yt
upon
minus
n.
1. And instead of alpha
The
into
beta
1
hat
minus phi, you have
GLS
alpha into
estimator
1 minus phi
in
hat.
this case is
Instead
also
of
called the
xt
weighted
minus
least
phi
square
xt minus
estimator.
1, you have xt
Why is
minus
it
phi
called
hat
that?
xt minus 1.
We will soon see.
Will give us an estimate of
So
phi
consider the
hat.
original model.
Once you obtain an
Yi is
estimate of phi
equal to
hat,
alpha plus
you
beta
simply
xi plus
substitute this
ei.
in equation 8.
We assume that
So
we
instead
know
of
sigma
yt
I,
minus phi yt
and so
minus
we
1,
divide
you
yi
have
by
yt
sigma I.
minus phi
So we have
hat
yi
yt
upon sigma
minus 1.
I on the left
And
hand
instead
side
of alpha
and
into 1
alpha
minus
upon sigma
phi,
I
you have alpha
plus
into 1
beta
minus phi
xi
hat.
upon sigma I
Instead
plus
of
ei
xt
upon
minus
sigma
phi
I on
xt
the
minus
right
1,
hand side.
you have xt minus phi hat xt
As you can
minus 1.
clearly see, because ei
Give us
upon
an
sigma I
estimate
is
of phi
nothing but
hat.
vi,
Once you
the
obtain an
equation in
estimate
the
of phi
previous
hat,
slide can be
you
written
simply
as summation
substitute this
vi
in
square
equation
is
8.
equal to
So
summation
instead of
yi
yt
upon
minus
sigma
phi
I minus
yt minus
beta
1,
xi upon sigma
you
I
have
the whole
yt
square.
minus phi
You can take
hat
out
yt
sigma I
minus
square
1.
common. So
And
you get
instead of
summation
alpha
1
into
upon
1
sigma
minus
I
phi,
square
you have alpha
yi
into 1
minus
minus phi
beta xi
hat.
square.
Instead of
Y
xt
minus
minus
beta
phi
xi
xt
square is
minus
nothing but
1,
the
you have
squares of the
xt minus
residuals
phi
of the
hat xt
original OLS
minus 1.
equation. All that is happening is each of the
Give us
sums
an
is being
estimate of
weighted by
phi
the
hat.
reciprocal of the
Once you obtain an estimate of phi
variance
hat,
of that
you
particular
simply
error term.
substitute
So
this
error
in
terms which have a large
equation
variance
8.
actually get a
So instead
relatively
of
smaller
yt
weight
minus
in
phi yt
calculation of beta
minus
hat
1,
GLS, while the
you
error
have
terms which
yt
have a
minus phi
relatively smaller
hat
weight
yt minus
actually
1.
get a higher
And instead of
degree of
alpha into 1
importance
minus
in
phi, you
calculation
have
of
alpha
beta
into
hat
1 minus
GLS.
phi hat.
In the OLS
Instead of
model,
xt minus phi
all the
xt
error
minus
terms
1,
have the
you have
same
xt minus
weight.
phi
You
hat xt
minimize
minus
summation
1.
ei square. Whereas for the GLS, we
Give us
minimize
an
summation
estimate of
1
phi
upon
hat.
sigma I ei
Once you obtain
square,
an
where
estimate of phi
sigma
hat,
1 upon
you
sigma I
simply
squared ei square,
substitute
I'm
this
sorry,
in
where each
equation
of the
8.
sigma I square
So
gives
instead
you the
of
variance
yt
of that
minus phi
particular
yt
ei square.
minus 1,
So each of
you
the
have yt
squared
minus phi
errors
hat
is
yt minus
weighted
1.
by
And instead
the
of alpha into
reciprocal
1
of the
minus
variance
phi,
of that
you have
error
alpha
term,
into
and
1
this
minus phi
weighted
hat.
sum is what
Instead of
we
xt
minimize
minus phi
in
xt
weighted least
minus 1,
squares,
you
which
have
is
xt
nothing
minus
but
phi
the
hat xt
GLS
minus 1.
estimator in this case.
Will give us an estimate of phi hat. Once you obtain an estimate of phi hat, you simply substitute this
Fine.
in
So if you
equation
know sigma
8.
square I,
So
you
instead
can
of
always
yt
do
minus
this.
phi yt
But the
minus
question
1,
is,
you have
we don't
yt
know sigma
minus phi
square I.
hat yt minus 1.
In fact, we are
And
not
instead of
likely to ever
alpha
know
into
it.
1 minus phi, you have
So how does
alpha
one then
into
use
1
all
minus
this?
phi hat. Instead of xt minus So
phi
what we'll do
xt
now
minus
is
1,
we
you have
will
xt
make
minus phi
a
hat xt
strategy
minus 1.
for estimating sigma square I
They
for
give us an
every I,
estimate of phi
and
hat.
then we will use the
Once you
estimated
obtain an
sigma square
estimate of
I
phi hat,
in
you simply
place of the
substitute this in
original sigma
equation
square I
8.
to develop
So
a
instead of
feasible
yt minus
generalized
phi
t-square.
yt minus 1,
So let us
you have
start by
yt minus phi
specifying
hat yt
the
minus
variance of
1.
EI
And instead of alpha
as
into 1
some
minus phi,
function
you have
of
alpha
a set
into
of
1 minus
variables
phi
called
hat.
Zi.
Instead of
Now this
xt
Zi
minus
could
phi
be
xt minus 1,
some
you
external
have xt
variables.
minus phi
There
hat
could
xt
also
minus
be
1.
nothing but the
Give
variables
us an
xi,
estimate
which are
of phi
included
hat.
as independent
Once
variables
you
in the
obtain an estimate of
regression
phi
equation.
hat, you simply substitute this
More
in
particularly,
equation 8.
let us assume that
So instead
sigma
of
square I
yt
takes the
minus phi
form
yt minus
of
1,
E being e
you
raised to
have
theta
yt minus
plus
phi
gamma
hat
xi,
yt minus
where
1.
xi is the
And instead
explanatory
of
variable
alpha
in
into
our
1
regression
minus
model.
phi,
Instead
you
of
have
this xi
alpha into
equivalent
1
in any
minus
other
phi
variable
hat.
zi,
Instead
it
of
could be
xt minus
e
phi
raised to
xt
theta
minus
plus
1,
gamma 1
you have
z1
xt
plus gamma
minus
2
phi
z2
hat
and so
xt
on.
minus
But for
1.
simplicity, we are using e raised to theta plus gamma
Give us an
xi.
estimate of phi
Now,
hat.
if you take natural logs on
Once you
both
obtain
sides,
an estimate
then
of
we
phi
have
hat,
natural
you
log of
simply
sigma square
substitute this
I
in
is theta
equation
plus
8.
gamma
So
xi.
instead of
So
yt
start
minus
with
phi yt minus 1, you
estimate the
have
original
yt
equation
minus
in
phi hat
untransformed
yt minus
variables.
1.
The
And
original
instead of
equation was
alpha
y
into
is
1
equal to
minus
alpha
phi,
plus beta
you have
xi
alpha
plus
into
ei.
1 minus
We
phi
know that
hat.
because x
Instead
and
of
e are
xt minus phi
uncorrelated,
xt minus 1,
OLS
you have
estimators
xt
will
minus
continue
phi
to be
hat xt
unbiased
minus
and
1.
consistent. So use OLS on the original equations
Give us an
and obtain
estimate of
alpha
phi
hat,
hat.
beta hat and
Once
e
you
hat
obtain an
I,
estimate of
which
phi
is
hat,
yi
you
minus
simply
y hat
substitute
I,
this
which
in
is yi
equation
minus
8.
alpha hat plus
So instead
beta
of
hat
yt
xi.
minus phi yt minus 1,
Step 1.
you have yt minus phi
Estimate
hat yt minus 1.
yi
And instead of
is
alpha into
equal
1
to
minus
alpha plus
phi,
beta
you
xi
have
plus
alpha
ei.
into 1 minus
Obtain
phi
alpha
hat.
hat, beta hat
Instead
and
of
e hat I.
xt minus
You know
phi
this can be
xt minus
done
1,
because
you
alpha
have
hat and
xt
beta hat
minus
will
phi
continue
hat
to be
xt
unbiased
minus
and
1.
consistent estimators because the covariance
Give us
x
an
and e is
estimate
still
of
assumed
phi
to be
hat.
0. In
Once
case,
you
of
obtain an
course,
estimate of phi
each
hat,
of the e
you
hat I
simply
squares
substitute this
can be
in
used as an
equation 8.
estimator for
So
the
instead of yt
sigma I
minus
square.
phi yt minus
However,
1,
this will not be a very
you
good
have yt
estimator.
minus phi hat
The reason
yt
is,
minus 1.
as the
And
sample
instead
size
of alpha into 1
increases,
minus phi,
you
you
actually
have
have
alpha into
more
1
and
minus
more
phi hat. Instead of
values of
xt
sigma I
minus
square to
phi xt
estimate,
minus
which
1,
means that
you
as the
have
sample
xt
size
minus phi
increases,
hat
the
xt
number
minus
of
1.
parameters that you have to estimate also increases.
Give us an
On the other hand, for
estimate of phi hat.
consistency, we want the
Once
sample
you
size to
obtain an
increase,
estimate of
but
phi
the number of
hat, you
parameters that you
simply
estimate to
substitute
remain
this
the
in
same or not
equation
increase as
8.
fast as the sample
So instead
size.
of yt minus phi yt
Therefore,
minus 1,
because
you have
each
yt
of the e
minus
hat
phi
I
hat yt
squares is
minus
being
1.
used as an
And instead of
estimator for
alpha
sigma
into
square
1
I.
minus
If you
phi,
have n
you have alpha
observations, you
into
have
1
n
minus
sigma
phi
square
hat.
i's to
Instead
estimate.
of xt
If you have
minus phi
n
xt
plus 10
minus 1,
observations, you have
you have
n plus
xt
10
minus
sigma
phi
square i's
hat
to
xt
estimate.
minus 1.
Obviously, the estimators cannot be
Give us
consistent.
an estimate of phi hat. Once you obtain an
So this is
estimate of
where
phi hat,
the
you simply
parameterization
substitute
log
this
sigma
in
square I is
equation
equal to
8.
alpha plus beta
So
xi
instead of yt
helps.
minus phi yt
In this
minus 1,
parameterization, we have
you
only
have
two
yt
parameters
minus
to
phi
estimate,
hat
alpha
yt minus 1.
and beta.
And instead of alpha
Once
into
alpha
1
and
minus
beta can be
phi, you
estimated,
have alpha
then
into
you
1
can
minus
form
phi hat.
estimates of log
Instead
sigma
of
square
xt
I
minus
by
phi
plugging
xt
in the
minus 1,
appropriate values
you
of
have
x
xt
in the
minus phi
regression
hat
equation.
xt minus
So the
1.
point is the number of parameters to be estimated drops from
Give
n
us
to
an
2.
estimate of phi
Now,
hat.
as the number of observations
Once you
increases,
obtain an
the
estimate
number
of
of
phi hat,
parameters
you simply
relative to the number
substitute
of
this in
observations
equation
will keep on
8.
going down,
So
and
instead
therefore
of
because you
yt
have
minus
additional
phi yt
information
minus
coming in,
1,
the
you have
estimators will
yt
become
minus phi hat
consistent.
yt minus 1. And instead of
The
alpha into
point
1
is,
minus phi, you
once
have
you
alpha into 1
obtain
minus phi
log of
hat.
e hat I
Instead of
square,
xt minus
then you
phi
regress
xt
the log of
minus
e hat I
1, you have
square
xt
on
minus phi
gamma
hat xt minus
theta
1.
plus gamma xi, where xi is a dependent
Give
variable.
us an
We
estimate
obtain
of phi
estimates of
hat.
theta hat and gamma hat from the
Once you
usual
obtain
OLS
an estimate
regression
of phi
and
hat,
get
you simply
log of
substitute
e
this
hat I
in
square
equation
hat,
8.
which is the
So
estimated
instead of
values
yt
log
minus
e hat
phi
I
yt
square,
minus 1,
from which
you
we
have
use these
yt minus
values
phi hat
to
yt
find
minus 1.
an
And
estimate
instead of
of
alpha into
sigma
1
hat
minus
I
phi,
square,
you have
which
alpha
can
into
be
1
obtained
minus phi
by
hat.
e
Instead
raised
of
to
xt
log
minus
of
phi
e hat
xt
I
minus
square
1,
estimated
you have
xt minus
so you
phi
raise the
hat
left
xt
hand
minus
side
1.
of theta hat plus gamma hat
Give us an
xi
estimate of phi
to
hat.
E and obtain
Once you
estimates
obtain an
for
estimate of phi
sigma hat
hat,
I square.
you simply substitute this in
With this step,
equation
you're almost
8.
there.
So instead of
Now that
yt
we
minus
have
phi
sigma hat
yt
I
minus
squares,
1, you have
they can
yt
be
minus
used
phi hat yt
to
minus
transform
1.
the variables
And instead of
xi
alpha
and
into 1
yi.
minus phi,
So
you have alpha into
instead of
1
having
minus phi
xi
hat.
upon sigma I,
Instead of
we
xt
do
minus
xi
phi
upon
xt
sigma
minus
hat
1,
I, which
you
is
have
xi
xt
star.
minus phi hat
We do
xt
yi
minus 1.
upon sigma hat I, which is yi star. And then
Give us an
we
estimate of phi hat.
we use these variables
Once you
to
obtain an
do the
estimate of phi
original
hat,
regression
you
and
simply
obtain beta
substitute
hat
this in
FGLS and
equation
alpha
8.
hat FGLS.
So instead of yt minus phi yt minus 1, you have yt minus phi hat yt minus 1. And instead of alpha into 1 minus phi, you have alpha into 1 minus phi hat. Instead of